revolutions per minute. The amount of times the crankshaft makes a full rotation of 360 degrees in 60 seconds. This unit of measurement directly affects the sound we hear out of the exhaust, the power we see on a dynograph, and the long-term survival of an engine. Internal combustion engines can operate within a broad range of RPM. 7,000 RPM in pushrod V8s like the LS7, 9,000 RPM in the F20C found in the S2000, and everywhere in between. When you spin an engine faster and faster, you reach a point of diminished and even negative returns. The torque it takes to overcome high RPM frictional forces, combined with a minuscule window for air to enter into the combustion chamber, leads to a decrease in output, which you will see on a dynograph as the power tapering off. Pushing past this warning sign can lead to a rapid, unscheduled dismantling of the engine, with the possibility of a connecting rod being sent into orbit. Luckily for us enthusiasts, there's ways to delay this power loss, push those RPMs even higher, and make more power for longer in the process. Using lessons learned from nearly a century of racing engines from F1 and NASCAR, we will dive into how to make your engine rev higher and possibly bankrupt yourself in the process of doing it. Welcome to Explained. To really understand the dark arts of extremely high RPM capabilities, we have to look at Formula One engines specifically during the 2006 season. This is where you see some of the highest revving engines ever in motorsport. The technical regulations for V8 engines were 2.4 liters in maximum displacement, a bore limit of 98 millimeters, which implied a 39.8 millimeter stroke at max displacement, and most importantly, no rev limits. With these restrictions, engineers were forced to spin these engines to insane RPM, since mathematically speaking, a horsepower target just equates to torque times RPM divided by a constant of 5252. By increasing either the torque or RPM, it will deliver a higher horsepower output. But with regulated displacement to 2.4 liters, which is directly proportional to the torque, the other way to get more power is to spin the engine higher, much higher. The Cosworth CA is a perfect example of this, being the first F1 engine to rev over 20,000 RPM on track, producing 755 brake horsepower at 19,250 RPM and 214 pound-feet of torque at 17,000 RPM. While the engine was a feat of engineering in itself, the Williams FW28 it was attached to was far from stellar, suffering from handling and reliability issues throughout the 2006 season, and it didn't let the Cosworth CA live up to its true glory. The Cosworth and other F1 engines of this era give us a lot of insight into building higher RPM capable engines, most importantly, their rotating assembly, the valve train, and the tuning of the intake and the exhaust. The first area to unlock high RPM potential is in the configuration of the crankshaft, connecting rods, and pistons, which different ratios between the bore and stroke and material properties will ultimately help or hinder your quest for high RPM performance. In reciprocating piston engines, the pistons themselves are subjected to extreme acceleration and deceleration G-forces as it reciprocates, and they get proportionally higher the faster you spin the engine, up to a point where the piston will ultimately fail. F1 engines and many factory high RPM engines use an over-square bore and stroke configuration, where the bore diameter far exceeds the stroke length, which the larger diameter bore allows for the use of bigger valves for adequate airflow in a short window during higher revolutions, and the smaller stroke decreases the average piston speed in comparison to longer stroke configurations. The Cosworth CA used a bore and stroke of 98 millimeters by 39.77 millimeters and a bore and stroke ratio of 2.5 to 1, which is extremely over square and produced an average piston speed of 22.5 meters per second, which is actually slower than what you find in an NHRA Pro Stock V8 engine, which has an average piston speed of 34.6 meters per second. The difference is the F1 engine needs to survive for a longer period of time compared to an engine used in quarter-mile drag racing. Therefore, the Pro Stock V8 can have insane piston speeds since fatigue is lesser of an issue compared to hours of runtime for qualifying and multiple races per engine in F1. Equally important as the decreased stroke length of the crankshaft is the material properties of the pistons, connecting rods, and crankshaft. The Cosworth CA used a forged 2618 aluminum piston in which the forging process creates a more uniform grain structure in the metal that is resistant to crack propagation in highly stressed areas, especially around the pin bore, and the aluminum alloy is lightweight compared to a steel piston, which will create high inertial loads on the crank journals, leading to rapid bearing wear and self-destruction at 20,000 RPM. The Cosworth engine's connecting rods were a little more exotic, being comprised of titanium alloy, which titanium offers the best strength to mass ratio between aluminum and steel, and while 4340 steel offers higher tensile strength or resistance to stretching when compared to titanium, the titanium rod will be approximately 20% lighter, further reducing the inertial loads on bearings and journals at higher RPM. The crankshaft under technical rules was limited to iron-based alloys, but a material like aluminum, even though lightweight, couldn't be used since it doesn't have a fatigue limit or endurance limit, meaning over millions of cycles it will eventually fail from even the smallest stresses applied to it. Steel and titanium, on the other hand, have a limit where, if not exceeded, the material can withstand infinite stress cycles, in theory at least. From a rotating assembly standpoint and over square bore and stroke configuration, lightweight forged aluminum pistons combined with high tensile strength connecting rods and crankshaft is the first building block to a high RPM engine. The next area of focus is the valve train, arguably the most important since crashing valves into pistons at high RPM isn't a long-term solution for any engine. Your traditional American overhead valve or pushrod V8s like the LS and Hemi that want higher RPM capabilities need to adopt an approach similar to NASCAR and NHRA engines, and dual overhead cam engines like Coyotes, Honda K-Series, and JZ engines need to adopt an approach similar to motorcycle engines. The enemy of both systems is valve float, where at higher RPM, the valve movement is no longer directly connected to the camshaft's lobe. P equals mv, remember that middle school science equation? Anything with mass like the valves and velocity like valves in motion also have momentum, and to keep that momentum in check, higher spring rate valve springs are the ticket. Spring rate is the pounds of pressure while open, or max lift, minus pounds of pressure at installed height, or valve close, divided by the valve travel distance. The higher the spring rate, the higher revolutions per minute you can achieve before floating the valves. But the increased spring pressure will actually create more power loss at higher RPMs as they increase parasitic loss within the engine. That's why, combined with stiffer, higher quality springs, you will also need a more aggressive camshaft grind with more duration and lift to move the peak power higher in the RPM range where those efficiency losses occur. These springs have different configurations as well. Beehive or conical springs allow for more valve lift before coil bind, which you want at least 50 thousandths clearance between maximum lift and coil bind height. And dual and triple valve springs help reduce oscillations in the spring at higher RPM and have an added redundancy. If the outer spring breaks, the valve doesn't drop into the combustion chamber and destroy the engine. Pushrod engines, generally speaking, will have a lower ceiling of RPM since there's more mass carried in the valve train. While simpler, the pushrod, lifter, rocker arm, and two large valves all carry increased mass which have more momentum to control than dual overhead cam engines with four smaller valves and the lack of pushrods. F1 engines like the Cosworth CA get around this predicament with pneumatic valve actuation. Rather than a steel valve spring, it uses air pressure to close the valves, and unlike mechanical valve springs, they are not subject to fatigue failure or diminished dampening with runtime like mechanical springs are. As you can probably already guess, this is a far more expensive valve train design, which is almost exclusively used by F1 and MotoGP, but the main takeaway is stiffer valve springs, lighter valves like hollow stem stainless steel or titanium, combined with a more aggressive camshaft profile to move peak power higher in the RPM band is the ticket. What ties all this together is air moving in and out of the engine. What's the point of spinning it faster if there's no more power being made? The denser the air getting in the engine and burning more fuel to that air will result in the most torque at that engine speed. And depending on the length of the runner, this will either make more torque earlier or later in the power band. Longer runners are best for lower RPM torque production, but become too sluggish to move air at higher RPMs, so for increased engine speeds, you'll typically see short intake runners that are tuned for those pressure wave dynamics at higher engine speeds. The aforementioned Cosworth CA engine has very short intake tracks since it runs all the way up to 20,000 RPM with a large plenum volume for the best air distribution per cylinder. In factory intake manifold designs, they account for spatial constraints, NVH reduction, and fuel efficiency more than all-out power. So when looking to push your engine to higher revs than the factory intake was designed for, it will need to be swapped for a short runner individual throttle body style intake and plenum that feeds cooler dense air from outside the engine bay into the intakes. When it comes to the exhaust, I made a video that's pretty detailed on the pulse wave tuning of exhaust manifolds and scavenging effects during valve overlap, and I'll link the video here, but to summarize, you want to calculate the rough primary pipe diameter of the primary runners for the least back pressure possible and adequate velocity for the RPM, and separate the pulses to reduce reversion back into the adjacent cylinders. Simply put, you don't need back pressure. You want exhaust velocity, and for a higher RPM engine, you want good velocity at higher RPMs, which by default means poor velocity at the low end. The biggest hindrance for a high RPM engine is the amount of cubic dollars you need to retrofit your production engine to reach 10,000 or more RPM. For the price to make a 10,000 RPM capable engine, you can probably add a turbo or supercharger and make the same if not more power. Forced induction is the answer to the problem, but just like Formula One, even though the newer turbo engines are more advanced, make a broader power band, and are faster, there's still a yearning for the older naturally aspirated V8s, V10s, and V12s to return. But if you plan to go down this path of revolutions over rationality, be prepared to empty your wallet faster than the engine can consume them.